So in graphical interpretation, the continuous time convolution can be viewed in the same way what we see in discrete time. So say that there is a signal. Remember, in discrete time, we say if you apply input, if you apply impulse as an input, we pick a point at each point of the system. In case of continuous time, we do it in a similar way with a very, very small time interval. So assume that we apply an input of delta to the system having x. We have impulse at a certain point, and this one will multiply to corresponding amplitude of the continuous signal. And the output of multiplication, which is this, is the amplitude at this point. If you apply the delta at this point, they will be multiplied by the amplitude at that point and will given as the amplitude of that point. So in here, and then you have a lot of those impulses. If you add them together with minimum and very small time interval, then there will be the representation of x. If you make those intervals small, small, small until they reach to 0, you can have a continuous representation of the signal. So you can view this one as in this way. If you have certain tau, this tau and t is different. T is general coordinate and tau is a time domain that is this delta t minus tau and xt as tau exist. So let's have a more viewed in it. This is the mathematical representation that we just described. So we described that in the same way to discrete time, we pick a point. We pick a point, add them, and make one more step in continuous time is make those intervals small, 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 so that they go to 0. So in here, likewise, this we also assume the linear time invariant system. We already so assume that we have a certain signal that is given like this. There is interval delta. The k delta means kth interval signal, and we multiply them by delta function at that k delta, and we multiply them by delta because we have to scale them. Assume that this is our input to a system. Likewise, what we do in discrete time, we put this input to a system, assume the output of this system is y. Note in here there is hat, the system, on the signal. This one means that we don't know the signal yet. We just put more freedom, more arbitrary characteristic to the signal. So we put that in here, put these signal to here, and then likewise what you do, as this is linear time invariant system, because it's linear, we could take out this xk, which is initially inside here, right here, initially inside here, you can take that out from this system function, because this is linear system. In linear system, we can take out addition, we can take out those constant. So because using the linear characteristic, we take out this thing outside. And then this one looks like when the input is delta function, what is their transfer function, which is we can define them as h, the system response. Impulse response is what? When input is delta, what is the output? When input is delta, the output will be if this output will be the same with the system itself. So we can define them as system response at point k delta. In here we have used a linear characteristic. Now we are using time invariant characteristic. If this one is delayed by k delta, if this one is time invariant system, the output does not change by time, meaning that if the input is shifted by time, output simply shift by time, but their form does not change. Using those characteristics, this one is impulse response delayed by certain value, so there will be the same to, I'm sorry, this is t minus tau, t minus tau. So it will same to some certain delay, which is corresponding to tau in this case. As this also, we need another function, say that the spacing is, we pick a point and make the spacing smaller until they go to 0. Using those characteristics, this delta will be d tau. This one becomes t minus tau because this k delta goes to tau. That's how things are go. Another way you can think is like this. To understand the X, the output response, we want to have, I'm sorry, this is not t minus tau. This one itself shows tau in here. So this one says here is, we have not used time invariant yet. We have h tau t, meaning that this h response is delayed by tau. Still, we have not used time invariant characteristic yet. The next page, we'll use time invariant characteristic. Now, those tau, as in time invariant system, when input changes by time, the output also only shift by time. Using those characteristics, we assume that this output, which is input is delta, this one is only shifted version of original value ht. So we can define the convolution integral like this. So what we have done by far is very similar to what we have in discrete time. In discrete time, remember, we have in discrete time, we studied that the output response will be the transfer function input is x. To get x, we have this value, which is pick a point of each point of x using delta function. And then using the linear system, we take out those summation, we take out those multiplication in a sequence, because in linear system, those addition and those constant can be taken out. That's linear characteristic. And we define this transfer function when input is a minus k instead of k as hk before. And then assuming the time invariant, this hn, we assume that this is a time shifted version of each other. But if this is time invariant, they can shift by time without changing it. So we can define them as time shifted version of original value, original function. That's how we do it. And using those two, we finally derive the convolution. This is sometimes called convolution sum, because we are adding together. This convolution sum is, we have this k, this one, multiplied together, adding from minus infinity to infinite to get y. Likewise, in continuous time, in continuous time, we define x. We define x by addition of each point of x by using delta. We multiply x by delta at each point. We have sequence of x. And then in discrete time, we added each point of x, which is given as first one. We apply a delta function to get each point of x, add them together to represent x. Put this x to input of the system. Output of the system is y, which is, if you put them, we can take out addition, we can take out the constant, multiplying constant, because this is a linear system. And then we define the transfer function right here as time-shifted version of HT. And then this time-shifted version, we have delta here, which is delta. This is triangle, meaning a spacing between one point to the other point. If we make this point closer, meaning that this delta, the different delta, becomes smaller. Then we can make them through integration. There's the only difference between linear discrete time and continuous time. And then we use time invariant characteristic of this and assume that this is only time shifted version of original value HT. Using those characteristics, you can define this one is only time shifted version of original function HT and find out the convolution integral in continuous time. So in case of convolution sum and convolution integral has similarities. Convolution sum is given as one value, one signal times the other signal minus k, adding from minus infinite to infinite. That's convolution sum of x and h. Convolution integral has similarity because I once explained that in discrete time summation, it will be integration in continuous time. So adding and x. Now there is a discrete time. In continuous time, they will round with a time, and h original value, it's right here, minus the variable used for this integration, the variable used for this summation. So basically they have same structure. Only difference here is some variables and then integration versus summation is only difference. The way we calculate convolution is very similar. In discrete time, how we do it, we fix one signal in k domain. We go back to example. We fix one. Now we are adding not in k in n, but we are adding k. We are integrating over tau, new domain. So in previous example in discrete time, we use a k and then fix one signal, reverse and shift another signal, begin to shift from lowest pace going up until they overlaps, find out when they overlaps, and then keep on moving until they no longer overlaps, and then find out the values at a certain point. In here, in continuous time is very similar. Let's have an example. Let's try to find what's yt if x is this, y is this. This is very similar to what we've seen before, right? So x is what? Exponential minus at when a is larger than 0. Then the table looks like this. This is xt. Okay, it looks like this. Now we also have unit function e minus at times unit function. Unit function is what? They are larger than that. They are 1, larger than 0, larger or equal to 0. Other than that, they are 0. Therefore, this one is like this. In here, below 0, they are all 0 because the unit function is 0. Then they become 1 from here and follow this e minus at. All right. What about the ht? Ht is unit function. So in case of main, the unit function is like this. That's our viewing example. And then to find a convolution, what we do, we pick one of them, maintain it. So now this one is no longer t, but they change to tau. They change to tau. So let's rephrase them so that the axis, the variable for the y-axis change to tau. So this one is function of tau. This one is x tau. And one of them is fixed. The other one we reverse. So let's reverse this. So there will be ht minus tau, which means this is reversed because there's a minus. So this one will be reversed. And this value t, right? And we add everything, remember in discrete time, we add everything from 0 to when tau or k is minus infinity to infinity and one value of n or t. We repeat that to find out all the values in y. So in here, let's do the same thing. Let's find output at each point, at each t. So let's start from the beginning. Let's put this one to lowest case, going up, and see that where is the overlapping. Where is the overlapping? So likewise, starting from here, until they hit at 0 point, until they hit here, there's nothing, no overlapping, so 0. So we can find out that when t when smaller than 0, then the value will be 0 because both either this or either this is 0. And then after they hit 0, tau equals 0, and they have like this. This area, this line, this tau, there's overlapping. Starting from 0 to t, right? So when t is larger than 0, now is what? Y will, this x will be e a minus tau. So x will be e minus a tau. What's the h? H will be 1. And then they will be integrated from 0 to t. Right? From 0 to t. According to tau. So let's rephrase this. We are actually adding from actually have x tau, which is here. We have h, which is here. And we are actually adding from minus infinite, tau equals minus infinite to infinite. However, they are always 0 from here to here, here to here. They are not 0 only from minus 0 to t. So actually this is from minus infinite to infinite. We are missing t to infinite and minus infinite to 0. In here, because the value is 0, we are neglecting it. So actually we are adding it all together. And what is it? What is it? What's the integration of EAT? Right? Here, right here. So we will have 0 to t, meaning that we have minus a 1 divided by a exponential e minus a t minus 1. That's the answer to this question. Is that it? Yeah. But don't forget, in this example, we have these conditions. So you can either say this one is this value when this larger or equal to 0, and otherwise all t is smaller than 0, they are 0. You can say like that. Or another way you can do it is using the unit function. Just one way like this, right? So you can either do this either way. You can have a condition. This condition is this condition is just like that, or you can use the unit function to say it. Let's bring a bit more complicated example, like this. Is it questions? Questions? Okay, now the problem here is x is like that, y is like that, h is like that. X is from 0 to t, they are 1. In case of ht, they are triangle. From 0 to 2t, they are t. Other than that, they are 0. So this is the original signal. So let's pick one of them fixed and one of them shift. Okay. So we fix this, and then we shift that. Of course, you can do the other way if you want. So let's fix this. So let's change this one to tau. And make this one to be t minus tau. So let's reverse shift. So this will be reversed, right? And this value will be t, right? So you can think them in this way: t minus tau equals minus t tau minus t. This one is the value of x or y or t. This one is constant in this case. So we can think them as minus x minus a function. What is it? We reverse and shift by a, right? So we can think that we reverse and shift by t. That's how we do it. So now we have a t here, and remember, what's the distance in here? There will be 2t. So it's this value of t minus 2t right here. Okay? And then let's start from the lowest case. Let's move this triangle for lowest case to here until this t hit 0. There's nothing overlaps, which is it's not showing here. There's no overlapping, so when t is smaller than 0, then output will be 0. Let's move this one. Remember that I will draw down here, say that uppercase t, lowercase t minus 2t. Okay? If you move that, begin to overlap. That's too much. Begin to overlap. Now, if this one, which is t, maximum point is t, right, is between 0 to t. So when t is larger than 0, smaller than t, for example, what is it? Now we have to integrate over 0 to t, small t, right? So overlapping what happens from here to here, like this. What's the value? That will be the slope of this. If you have on a triangle, they move, they shift larger than t, but this lower case, which is 2t minus 2t, is smaller than 0. What happens? So remember, this length is 2 large t. So this is 2 times longer than this. So when they overlaps, even though the uppercase comes outside of this area, the lower case, which is here, still maintain as smaller than 0 because this length is 2t. So second case is when t in uppercase is larger than t and t in lowercase smaller than 0. What is the case? T is and then t is smaller than 2t. Let's put this. This second case, now all of this area from here to here, which is 0 to large t, they are overlapping. So integrate over like this. Case 1, case 2, case 3. What about case 4? When this one, now assumption is the lower part of this triangle is smaller than 0. When this one is larger than 0, but still inside this area, what's the case? If this lower case, which is t minus 2t, smaller than t, larger than 0, what's the case? There will be 2t t is the case, right? In this case, overlapping area is from here to here. Here is t minus 2t, here is t. So we are integrating from t minus 2t, 2t. And what's the 5 case 5? T is larger than 3t. There will be 0. No overlap. So that's how this picture shows. And you can calculate them. What is this value? What kind of function should we put in here? What kind of function should we put in here? What is this slope? What is this function? What is it? So you can think in this way. Initially this h is what? Y t equals just t. Right? In here, we switch this one to let's have h tau minus t. Right? Now this is what? Tau minus t. I'm sorry, t minus tau. Right? One thing make me confused when I first learned about convolution when it was 1999. This makes me get confused because originally it's t, now the t is constant and tau become a variable. They make me very confused. But you can think this way. Say this is x. Now this one become another variable x tilde, and this one only become a constant. So you can think that this way. So you put them in here, t minus tau. How do we calculate? Let's erase this one a little bit. If you integrate this, remember t is constant, tau is variable. So when you integrate that, it will be t times tau minus 2 over 3, tau squared. Right? From 0 to t. This is what? T squared minus half of t squared, so it will be half of t squared. That's what the first one shows. As this integration will be the same, in here you change this to 0, you change this t to tau, to change this small t to t and integrate again. We do the same thing until you find the value. That's how we do it. So basically, both discrete time, both continuous time do the same thing. We have two signals in linear time linear system. There's convolution, defines the output, find the output using the response of the input signal and the system response of the system, H. We pick one of them, fix and change its variable from n to k or t to tau, pick another one and change its variable from n to n minus k or t to t minus tau, multiply them and add in discrete time, integrate in continuous time from minus infinity to infinite. How we do it in graphically, we pick one of them, change the axis, the other one flip, shift by t or n, and starting from the beginning, we begin to shift by t or n from the lowest case to upper case until they first overlaps. If those overlapping area changes, we divide by those area until they leave and there's no more overlapping happens. That's how we find the convolution sum or convolution integration. Okay, so that's a summary. again and again. Every assumption we use linear characteristic and time invariant characteristic. So this convolution sum or our derivation by far only valid when linear time invariant system. In case of discrete time, they're given as convolution sum. In continuous time, they're given as convolution integral. Questions? Okay. All right, so convolution has several characteristics. They can be communicative, meaning that you can switch. So you can have xn, hn, or hn, xn. You can reverse the order. They are associative, meaning that if you have a multiplication and plus, minus, you have priority of multiplication or dividing first, and then do the plus and minus later. In here, there's no relationship like that. You can do this one first, or you can do first one first. So that's what I'm saying. Distributive is when you have multiplication, convolution of one thing, have two systems, you can do addition first. Note, this is a system. This is a signal, right? So if you can think this way. I will explain next page. However, remember our box. Remember that we have a system response before. Talking about series and parallel systems. We have a series system, right? Remember? There is H1, H2. The total system will be what? H1 multiplication of H2. In case of parallel system, we have H1 plus H2 will be system of all of this. Remember, right? This one go back to the story. In here, we use large capital word H instead of small h. Meaning that in the first day of the class, I define several notation we will continuously use in this lecture. If this is capital, that means that's frequency response. This H, you remember that they're usually given like this, or they're given like that, right? This S is frequency component, not T. This omega is, of course, the frequency component. So this H, large H in here, they are a system or frequency signal given in frequency domain, not time domain. The thing we see in here, they are small h, and they are given in time domain. They are signal, they are given in time domain. Remember, we once briefly talked that the frequency domain and time domain has similarity. What happens is there's one relationship changing from time domain to frequency domain. The other way happens normally. They have a lot of similarities. If you see like that, if time domain, let's rephrase this one a little bit. Let's rephrase this one. Assume that we have system response in time domain small h1, small h2. They will be shown in here actually. Okay? The first case is time domain signal, which corresponds like this. and this one is parallel case, right? But the difference between what we learned before and this case is the thing we briefly described before is time, not time domain, but frequency domain, given as large h. In here, we are talking about time domain, which is given as small h. How to calculate? Let's go back to what we have learned just before. To find out, say this is output of t. I use the discrete continuous time, but the same principle, same explanation can apply to discrete time also. So assume that we have input of xt in time domain. What will be the output in here? How do we calculate the output? Yay. No, this time. How do you calculate the output? Like this, right? To find this first output, we have to integrate from minus infinite to infinite x tau times h t minus tau dt, right? What about here? What about the output in time domain here? We have now, we are integrating, we do the convolution between, input is now what? y1t. This was now input. So y1 tau times h2 t minus tau dt, d tau. This is how we find the output. So how we rephrase it, we can have the first one we can rephrase them as xt convolution h1t. This is what? y1t convolution h2t, right? And then this and these are the same. So let's switch to get this. You will find what? X t convolution y h1t convolution h2t. Looks very even more complicated. So what's the similarity between this and that? Let's rephrase them this one a little bit. As we just learned that this one we can switch the order, we can change the associate, we can distribute like that. How you find it? It will be, let's put this one first, convolution, put this one same way, and put this one the last part. And let's put like this. We can think this one as, this is the output, final output of the system. This is the first input to the system. This input goes to this one system having this red box here. So you can think that in here we multiply. They correspond. This is frequency domain. In time domain, this one corresponding to H2. Of course, you can switch H1 convolution over H2. So what? Convolution, they have same meaning, same system, talking about same meaning. Convolution in time domain correspond to multiplication in frequency domain. Okay. Likewise, convolution in frequency domain correspond to multiplication in time domain. So that's how it works. But we barely use multiplication in time domain. That's a very special case. We normally have a series of systems or parallel of systems like this. And the reason that I say convolution is one of the most important concepts in this lecture, because convolution gives you an idea that the relationship between the input and output in time domain, right? But you can utilize this one as multiplication in frequency domain. That's the reason we learned that we transfer to frequency domain and calculate in frequency domain and go back to time domain. Why? Because there's many reasons. One of the reasons is, if you remember our calculation before, this is a very simple system and signal, right? This is a very simple system and signal. To calculate the output of the signal system, we have to pass through a long calculation, relatively long calculation. If system becomes more complicated, it will be even more complicated. It takes a lot of effort. But if you can change this one to corresponding frequency domain signal, you don't have to do the convolution to find, but you have to do the convolution to, the convolution is how to say, you have to do it. We don't care about what happened. We don't want to know the output. Always, if the input and system is given, we want to have the output. But to get the output, we have to pass through very complicated, very long, tedious calculation to find the convolution. So one way we can retrieve those tedious efforts is, let's find a frequency response. Let's find frequency response and calculate in frequency domain. We just multiply them. You don't have to do the convolution. And go back to time domain. Or you can still analyze in frequency domain. That's one of the reasons we learn the frequency domain transfer function between time frequency time. So in here, what we learned is, if you have a series of system, we can do convolution of these two, which is the system response representing these two systems together. Likewise, if we have a parallel system in time domain, we can consider them as like this. So that's how this property explains. Let's have some physical meaning of these mathematical properties. In here, in commutative meaning, that means that there's no rule that X is always input. Sometimes we can call them as H. Sometimes we can call them as, I don't know, A, a triangle A, N will be the signal. So that means if X is the input, assume that this is the input. The later one is assume that if H is input to the system X, output will be the same. Understand? So previous case, we have a definition that the box is H, we have input of X, output of Y. If you reverse, if a box of X, system response X, input as H, then output will be the same. That's the meaning of this commutative property means. Associative means that, like this. If you have H1 first, H2 later, in linear time invariant system, you can switch the order. If this one's H2, this one's H1, output will not change. This is the interesting and important characteristic, because if you have some sequence of system, if you switch the sequence, the output doesn't change, they were the same. What's the meaning of the last one? Addition is what? Parallel system. This is what? Series system. So, what this one shows here is, you can have input of X to the system, which is parallelly connected, H1, H2 parallelly connected system. That's exactly the same system that this one, X go to one system and X go to second system, adding them later. Does not matter. That's what they shows. So let's bring up more graphical meaning. I just said the first characteristic, communicative, means that assume that this is the original system we have. We can have one system having like this, even though we switch them. Even though we switch the order, does not matter. Even though we switch the order, does not matter. That's what the communicative means. If you have parallel, as I said, there will be addition. Addition. If you have another system here, there will be same too. If you multiply, if you conversion first, add later, or do the conversion first and then add later. It's the same meaning. So you can redistribute the location of the box using these property equations. Okay. Questions? So in the linear time invariant system, let's have some other meanings. Memory. Memory versus memory list. What is it? Memory list is a system that only depending on the input at current status, right? We don't care about future. We don't care about the past. We only care about the current status. Think about if you're asked that this system is memoryless or not. What you have to find out is this one depends on the past or not. Okay? Let's think about this. Too many. Okay. So if you are asked that this is memoryless or not, let's bring up this. Let's think about that if this one and this one is non-zero at a certain point. To be a memoryless, we only care about current state, right? We don't have to think about the past. But this one becomes a problem. Remember, to do that in time domain, let's scale them together. If this is x, this is h, right? Because they are shift reversed. So if you want to calculate this point at time of n, they depend on the past because of this h. So this is basically memory with memory. This one requires memory because the h or x sometimes they shift, they reverse in time domain. Therefore, they are always depending on the past. Current is what? Current is n. N is here. They're only depending on here as a medium memory. However, because they are depending on the past, so they are basically with memory. Only one exception is when this one is always zero. When this one is always zero, and everything is flat. We already know that this is a zero. So we can consider them as memoryless. However, other than the case, is with memory, because they are shifted, they are reversed in time domain. How about invertivity? Invertivity means is what? The system characteristic invertivity means we have a system H, say that X is input, Y is output. We can figure out another system H2 and input is Y, output X. If you figure out this, then this system is invertible, right? So let's have an example. So this is how the invertible system works. Say that X is input, Y is output. When Y is input, X is output. If you can figure out this kind of system, then there will be the invertible system. So in short, we already learned that if we make this whole system together, what's the symbol representing this system together? There will be H convolution H2. There will be the system representing this red box. And if you redraw this red box, what happens now here is, if you have this red box, having this one here, input is X, output is X, right? If you redraw it, input is X, output is X is what? Right? So the question now changed to, let's find out if you can figure out H1 that make those convolution to be impulse. Then this system becomes impulse itself. If you do the convolution of X and impulse, that X will come out for sure. Because this impulse, they shift by time and pick each point of X. So X will come out as output in both discrete time and continuous time case. So our question can be rephrased as, can we find out convolution to be delta? So this is a judgment case in linear time invariant system, if this is possible or not. Let's have an example. Let's say example. This YT X is what? X. This is invertible or not? It's invertible or not? So the question is, remember, this is not X. This is not X. This is a system response, right? So this one is, please do not be confused, because this X is input, H is output, right? So there is no system information here. We have to figure out what is the system. So let's draw it. There's an input, there's a box which is H, which is output is Y. Why would the system response to make this? Let's replace X tau. There's X signal here, tau. Let's do the convolution, delta. now is what? At t, right? So what this one in this relationship, they pick up point of x at point of t, right? They pick up x at point of t. When t changes, they pick up different point. Now we want to have time shifted version of t. We want to pick a point that they shifted by t minus t0. T minus t0, for example. How we do it? We shift the impulse. If you intentionally make this impulse to be shifted, then even though t is fixed, we can pick a point at this point. How we do it? We change this. In here, initially there was delta t, and we change it to delta t minus tau. If you change this one to, say, let's start from like this, t minus t0, for example. We want to have things like this, right? To pick up at t minus t0. How do it? Let's go back to here. Then this part can be rephrased as t minus t0 plus tau, right? And then t minus tau minus t0, right? When we change the original signal to convolution form, I say, we put this one, the original one, to some constant minus x value, right? And now they are picking a point of t. When tau is t, they pick a point. We want to shift because we want to have different outputs, right? We want to shift. So we intentionally change this t to t minus t0 so that they pick up point when tau equals t minus t0. The point like that. And this one corresponding like this, we can rephrase them like that. So remember, they have a constant time minus x value like this, the constant minus x value. So there will be t minus t0. So we find our system response with the delta like this. Of course, you can intuitively find it. If you already know that they pick a point of t, you want to have shifted version of t minus t0, and you just, okay, that will be delta t minus t0. You will find that right away. But for just in case you have some plus or minus, plus t0 minus t0, some confusion, you follow the step, then you'll find out. So we know that system response is this one is delta t minus t0. Convolution of something is delta, then this one is scalable. This one is invertible. What is it? Now they're shifted by t0. What if you shift it again to this side? So if you shift plus t0, they shift back. So invertible system is what? According to our knowledge, invertible system is having another system. The input go back to the input. And from this analysis, if you find this relationship, find H1 to be delta, then this system is invertible. And if you find H from this calculation, and then you already know that HT plus T0, if you convert together, they will be delta. So that's the reason that this is invertible. So judgment factor, one of the judgment factor we have in the invertible system before is we just try to find arbitrary signal, arbitrary system, then may go back to the input. But in here, we have a little bit more systemic thing. Find something make convolution to be delta. Okay? And the causality. One more time, causality is what? Causality is they only depending on past and present. They are not depending on the future. Okay? So to be causal. To be causal, let's remember this. This n value, if transfer function is 0 for n is smaller than 0. So this assumption is basing on that what we have seen before. So if hn, many of the examples we have unit function after it. Unit function means they are 0 and below 0, right? If they are like that, yes. If they are not like that, not like that. For example, if you have some zeros, some non-zeros here, even though you reverse it, this one goes to where? If you reverse it, this one goes to here. So if this part is not 0, they go to the future if you reverse it, right, in convolution. Therefore, if this is not 0, they are not causal. To be causal, the value below 0 should be 0. Because when this one becomes h n minus k, this one goes to here, which is the future information. You need the future information to get the output, which is not causal. If it is 0, then there's a causal. Stability. So how we never discussed about stability before. We did not talk about stability. We just talk about that when a small input happens, if they go to a different state, there's a unstable. They are stable. If they go back to normal position, they're stable. One way we find stability is something called bounded input, bounded output. That's the characteristic that bounded input is like that. When input has, even the input is like this, they have a maximum, they have a minimum. That's something called bounded. They are bounded between certain points. If this is input, when output is also bounded in, of course, different value, then they can be considered to be stable. Of course, even though they are bounded, they can be moved inside here. However, they does not diverge. So we can consider them as stable. So bounded input, bounded output means that when input is bounded, we intentionally apply input that is bounded, then we check if output is also bounded. So assume we have bounded input. Assume we have bounded input. If we have bounded input in here, our output will be sigma x. Let's have some convolution, right? And then we have to find out the bounded if output variable is bounded or not. The same to here, right? And do you remember that the summation of everything is smaller than summation of each of it? So like this, a plus b absolute value, a absolute value plus b, which is bigger? 1, 2, nothing. Right? So we can replace them like sigma implication x minus k times h k. Right? And then this one is, as this is bounded, then we can replace them like this. What's the last part? What's the last part? So basically, we're starting using this equation. We put absolute value in whole thing, add each of the absolute value, and this absolute value is smaller than b, so we make them larger than b. So if this one is also bounded, if summation, the b can be taken out like this, it can be like this. So the summation of hk is smaller than infinite, then we can consider this one is bounded. That means this is stable. So there is sufficient condition that if this one is absolutely summable, this is something called absolutely summable, meaning that the summation of everything, the absolute value is smaller than certain value, then this is sufficient condition. There's also in continuous time, if each of them is absolutely integrable like this, that's also stable.